right, so today we started the last topic of the course, and I think when so after we cover some key aspects of linear regression, I might just go back to the hierarchical again a little bit. Mostly this is because many of you are doing regression type of project, and for meetings I noticed probably better if we can, and we are ready to cover it at this point anyway, so I think we're just going to start on this. So we're going to spend a couple of lectures on the simple linear regression where you only have one predictor, okay? And then we're going to spend, I think, another lecture on like multiple linear regression when you have multiple predictors. And then I think by then we probably will have time to go back, especially with the hierarchical. I wanted to go back to the video that Professor Josh Dileo did for us, and then there's certain questions I think were left unanswered at that point. So so that's the plan. But of course, if you have other comments, questions about hierarchical modeling, we can easily go back there. All right. So so to get us started, well, it's a relatively long chapter in this case, and the current version of the slide, I think I haven't included the multiple linear regression, but I will update it and let you know when it's ready to view or to download. And for us, I think we're going to start with a short introduction, especially building up based on what we know about the normal model that we did before, okay? And then how to think about, well, now pretty much, so linear regression itself is still based very much on normal model, okay? But then we're trying to add a continuous predictor variable, like when you have a predictor to be continuous, but later you can also do a binary or categorical predictor variables as you see fit. So as an introduction, let's think about, so this is equation 1 is where we used to have continuous outcomes, and we assume that each of the observation is IID, normal mu sigma. And notice that we're writing IID. So IID again stands for independent and identically distributed. So we use IID because they follow exactly the same normal distribution. Okay, that's back then in that chapter. So suppose now, and this brings back us to the consumer expenditure survey again. So if you remember, the outcome itself, the yi, at that time, we're looking at as the log of the expenditure of the CU. Okay, we did the transformation, so it looks more like a normal, so we can do the analysis. So suppose now you have another continuous random variable available, which is xi. We use small letter in this case because it's data. It's giving the data for us. And you want to use information in xi to learn about yi. So y, capital letter, we always use it for random variable. X or small letter for known data. So yi, just to remember, it is the log of expenditure. And for now, we're looking at the log of the total income, okay, as the extra information that we know about the CU. So how do you think that we can do some flexibility about this equation 1? How can we include the extra information about the CU? That is their log of total income, to help us learn about the log of expenditure. Okay, so I know many of you already have exposure to linear regression in one way or another in other courses, but I do want you to talk with your neighbors about your understanding or approaches. In particular, how can we update or change our model in equation 1 to include the extra information about CU. Okay, so the goal, the outcome, is the learning about the log expenditure. So in addition to that, we also know the consumer units total, a log of total income. So we're trying to figure out if that can help us learn better about the log expenditure. Okay, so let's take a few minutes so you can talk through. If you already have coursework related to this, try to write it out based on your understanding of what the model would look like. So you forget it. Okay. Come on, you failed. I did. Come up with any ideas to include the information about that we know about CU to learn about the yi? So how can we change our model in some way, and then how can we formally write it out? Anyone? Very heated discussion. One?
she talked about frequentist linear regression. So the basic idea is that you could do something like least squares to find the slope of the line that best depicts the relationship between the xi and the yi, and then have some sort of error intercept term.
Yeah, so that's good. So the thing is, if we start to write the model, so later you will see that the Bayesian model and the frequentist model will look very similar. It's just how you approach the estimation process will be different. Okay, so if we're going to try to include xi into our model, then equation 1, this IID model actually going to become what we call not IID anymore, but independent. But then you're going to have observation specific mean to do that. Okay, so you probably have heard about those terms, like say, it's really about the expectation of the response, right? It's a linear combination of the terms that you have. So you may have seen things like this. I'm just going to write it out. And then the yi itself follows a normal distribution, or you can write, erase this. This one. Going to be beta 0 plus beta 1 xi, and then plus the error term, okay? And the normal model really comes in about this error term here. Now the error term typically is IID, normal, 0, and sigma. Okay, so this will be, I think, what you probably have seen before. Okay, and then the least square that Caroline talked about is how to estimate this model itself. Okay, so the Bayesian approach, well, is actually no much different. And we actually going to write the model in the same way, but then we're going to use different approaches to do the estimation. Okay, so let me cover the basics now. So if you want to have an observation specific mean, because now you want to introduce the fact that we know something extra about each observation. So this is what you will do. So that's why I said earlier, IID will become independent, because IID, one of the I is meant to be identical, but they're not identical anymore. Okay? They are independent still, but then they have their own observation specific mean that we're doing. So that's why you're going to change the IID to be independent. But then the normal model still stays the same. We actually also assume the same standard deviation in the model, but then you are having a individual specific mean. And then the way to link the mean and the observation is through a linear function. So the linear function is in this equation 3. Okay, so that's why you have seen this in other contexts before, that sometimes it's beta 0 plus beta 1 xi, sometimes it's alpha plus beta times x1. So whatever, those two is what people usually call regression coefficients. Okay. And for notation, xi's, they are the known constants, or I wouldn't say, maybe I shouldn't say constant, but just observation. Okay, you know the data from each observation. But in our Bayesian approach, we're going to focus on taking or recognizing beta 0 and beta 1. They're the unknown parameters. They're coefficients, but they're unknown. And in Bayesian approach, not surprisingly, we're going to put prior distribution on them, right? And then later on, figure out what would be the appropriate posterior estimation of those parameters. Okay. So before we get to how to do the actual estimation, we need to get clear about some of the interpretation of the model. So first of all, if you just look at the mean, you notice that in equation 3, that's what we write, beta 0 plus beta 1 xi. That's what we call the expected outcome with xi, okay? Its own expectation. And that's why we use mean, okay? And also sometimes you see notation like this, the one that I just wrote before. Sometimes in certain contexts, people like to write the expectation of the observation. Okay, now we're using mu I, but they're all the same thing, so you can use things interchangeably. Beta 0 is what people typically call as the intercept. Have we heard this? That will be the expected outcome when your xi is 0. So if you look at mean, in equation 3 that we're doing here, if your beta 1, if your x1 is 0, xi is 0, then this whole term becomes 0. Then beta 0 is really just the expected outcome for an observation where its xi is 0. Okay? And similarly, beta 1 is what people call as the slope. It is the increase in the expected outcome when xi increases by 1 unit. So that, if you focus on the notation that we have in this equation 3, that will be, yes, so regardless of what beta 0 is, we just keep it there. But then think about, so beta 1 is multiplying with xi. So if your xi increases by 1, then your whole mu I term going to increase by 1. Oh, sorry, by beta 1 itself, right? So that's the effect of what we call the increase in the expected outcome when xi increases by 1 unit. Okay, so this kind of notation, or I would say interpretation, is probably very familiar to many of you. But again, whenever we're working with mu I and then this linear function, it's always talking about the expected outcome. Okay, everything is on the mean. Okay, the extra thing about the normal is going to come into play when you're dealing with that sigma. And then the coefficients, the regression coefficients, beta 0 and beta 1 here, they're only about the mean. Okay, so that's why later when you do interpretation, everything is on average or by expectation, that kind of notation. All right, so the Bayesian approach, not surprisingly, we're going to assign prior distribution. And don't forget, not only we have beta 1 and beta 0, they're the unknown parameters. Sigma itself is unknown as well. So we're trying to make inference about it as well. So right now, I'm generically writing that we're going to assign a joint prior distribution to all of them. And then we use our MCMC technique. Later, you will see that we're going to rely on JAX again. But for some simple models, you can actually derive the full conditional posterior distributions for all of the parameters. So if you want, you can also do your own MCMC script if you want. And then after that, the last step is summarize the posterior distribution of these parameters. Okay. And again, we will get a bunch of draws about each parameter. You're going to do the thinning, all that, to make sure that MCMC diagnostics are passed. And once you get to that point, you can like return the mean, the median, the 95% credible interval, all that kind of stuff about those parameters. So those will be the key that we're going to focus on in terms of summarizing the posterior. Okay. All right. So if we put everything together, depends on how you like writing the model. Equation 4 will be like putting all of the information together, as you can see. So we replace the mean mu I using the linear function that we talked about. And then, so this kind of way of writing the model also focus on, like put an emphasis on the sigma itself. Okay, we're not only just looking at the expectation, but also the sigma, the standard deviation in the model. And 5 through 7 would just be another way to write the model. It really depends on like what kind of text you're reading or like other exposure that you have. So for our course, the purpose, I think I just try to introduce all kinds of notations that maybe one way or another you have seen before, but try to make the connection to the other stuff that you have seen, especially if you know how to do the frequentist inference, and then later you might be able to see like making some kind of comparison to what we have done. Okay. All right, so before we move on, what kind of assumptions does this model make based on either equation 4, the way that I write that model, or alternatively through 5 to 7? Can you talk to your neighbors about the assumptions that you think this model is making? We know it's a normal. We also know the mean is being linked to the predictor, the xi, in this particular way. So I do want you, just to like brainstorm to make sure that we know what we mean by this model before we move to do the actual inference. Okay, so maybe talk to your neighbors for a few minutes. All right, so let's hear from some of you. What do you think the assumptions are being made when we write our simple linear regression model setup that we have here? Anyone? Josh?
I noticed the slope, and so I guess the beta sub 0 and beta sub 1 are consistent throughout different values of mu I, although xi changes depending on subscript.
Yeah, so in fact, not only the beta 0 and beta 1, but also the sigma, all of this are being shared. Okay, and as you can see, the subscript that you have, well, each observation has a index, that's fine. And then we also have the predictor is being indexed by each observation, that makes sense as well. but the model does share all of this together. So that's why, well, the 3 parameters will be estimated through our Bayesian estimation process, but it's important to recognize that they're being shared across the observations. And especially, I guess, if we now link this back to what we did in the hierarchical modeling lecture, that we know, well, it depends on how you're sharing the parameters, right? Like say, I think back then we're having each schedule or each group is having a particular mean, like mu j, right? But then sigma, the standard deviation of the data model, is being shared across all of the observations. Okay? But the mu j, the group specific mean, is only being shared among the particular group. Okay? All right, so that's a good observation, and that's important to realize. Anything else? Anything that you think we're making assumption about when we are proposing a model like this?
We're assuming that the errors are 0. The expected value of the errors is 0.
Yeah, so here, as you can see, the error, or the residual, sometimes people call that, epsilon I is IID normal, and the mean is centered at 0, okay? So that, I think the setup, especially if you compare the way that we write about this 2 different ways to express it, it is exactly because the mean of the error is 0, that's why you don't contribute to this, right? So the mean of the observation, as we know, by definition, is beta 0 plus beta 1 xi, and then, so you're adding this 2 up, right? When you are expressing your yi based on our equation 5, but then because the mean of the error terms is 0, and then you're adding pretty much just like a different function on top of that. And then this actually also goes back to if you took 241, and because you remember that when you're adding 2 independent normals together, it becomes another normal. Okay, whereas the mean is the sum of the mean, and then the variance will be the sum of the variance. Yeah. Yeah. So that's another thing here that is happening. Okay. Good. Anything else, or like questions, comments before we move on? We feel comfortable about the setup overall. Yes.
Is there a reason why we chose normal? Is it just because it's the easiest distribution we can play around with?
Yeah, so good question. So in fact, I think, especially in the Bayesian paradigm, you can actually use whatever model you want to do. And I should mention, well, whenever people are talking about linear regression, like by default, it's talking about this normal model. And then it is a linear relationship between the predictors and the observation. And I should mention what Caroline earlier was saying about all of those least squared, all of those results is based on the normal model. Right? Yeah, but yeah, now I think once you see the Bayesian paradigm, especially you're just like putting prior distributions for whatever parameter you can think of, then yes, it's not necessary that it's going to be a normal model. You can actually choose other ones. And maybe, yeah, typical choices people do like log normal is when they're dealing with strictly positive observations, things like that. And if you want, you could even do like gamma, whichever you want to do. So it's pretty flexible, I would say. But then I think historically, simple linear regression is defined to be a normal model. And then IID error with mean 0, a particular standard deviation that you're trying to estimate. And then it's a linear relationship between the predictor and the observation. Okay. All right. So yeah, of course. I mean, I guess a follow-up of that question is, well, we're dealing with, in this case, the log of expenditure, so it's continuous. So that's why you want to use a normal model. But there are many other cases, like if you have binary outcome, you probably have heard about logistic regression, and that's where you're putting a particular link function to the outcome, because the outcome has to be 0 and 1. Oh, 0 or 1, right? And I think the other day, one of the project team is talking about, well, if you have multiple categories of the outcome, so like binary, we know is 0, 1. But what if you have like 1, 2, 3, 4, 5, or like which has the order, or maybe you have like marital status, which is like different levels, but there's no order among them. It's just like different types. Then you should use other type of modeling approach. Okay, so normal model in this case is really just for continuous outcome. Okay. Yeah. So I think, yeah, I mean, some of the projects probably will touch upon those when we do it individually, but like if you have any ideas or questions, feel free to raise them up so we can discuss in class. And lastly, before we talk about the details of the estimation process, I do want to share this plot with you, especially if you just think about the model again really quick. It's yi independent normal beta 0 plus beta 1 xi and then sigma, right? That's the one way to write the model itself. So another assumption, if you think about this, is this the linear relationship between this and the mean. Yeah, over here. That's what that line is trying to fit. Okay, so the line is really just fitting the mean of each observation. And the sigma, I'll use a different color here. The sigma here is trying to capture the variability. Okay. Now you see why, I mean, I particularly like this kind of plotting, just to show that, well, the regression line is really just fitting through the mean. Okay. And then whenever we're doing a regression model like this, we're assuming that the observation is gonna be like center around that mean, right? But it can be anything in terms of, well, sigma itself gonna control like how large the spread will be, right? And that's one thing you want to estimate. So the mean is being captured by this linear relationship, but the linear model itself also has this random error. And that random error is trying to capture any kind of deviation that the actual observation is from the mean. Okay? So that's why in frequentist estimation, you probably have heard, yeah, like doing all of the least square, all that, but at the end of the day, you have to check whether the model is good or not, right? And many of you probably have seen the approaches of using doing a residual plot. Whenever they're doing residual plot, what they meant is that we're looking at the actual observation and looking at the difference of the observation from, like, say, the mean itself. So you're just looking at how big the difference is, and then you plot it. You want to make sure that it's going to be normally distributed, because that's one of the assumptions of the model. Okay, so that's, I mean, afterwards. But even just before going to that point, we should focus and also emphasize the assumption that we're making here is that the sigma, the normal model, is really being the normal part of this is each of this horizontal thing. Okay, but then the mean, the line that we're fitting, is about the average or the expected value of each observation. Okay, all right, so I think that's mostly about the model itself, and I do want to show you the data set that we're working with. So on Moodle, in our section, I posted this new data set, cesample.csv, and we're looking at the outcome to be the log total expenditure, and then the predictor is the log income. So right now I'm plotting just two-dimensional, the observation, or I should say the outcome against the predictor. Okay, so that's why many of you probably have seen that whenever we're talking about a linear model and we're talking about this linear regression line, the regression line is the mean that we're trying to fit. Okay, but then of course you see those deviations, right? Like the observations at like this point is not at that point, is not at that line. It is, well, having a difference. And all of those differences, all of the ones that you can draw from here, is trying to be captured by the normal model, because that's how, remember the previous slide, that we're trying to capture that deviation using the normal assumption, and that's the error term that we work with. Okay, so that, I think, altogether completes the understanding of all of the assumptions that we make when we're doing a simple linear regression. Okay. Alrighty, so you can later play with the data set a little bit more. And yeah, so I'm just going to combine this really quick together. The CE sample now we work with, I have 4 variables here for us. There are 994 observations in total. And the outcome is the log expenditure. It's going to be continuous. And we're looking at right now the log income for the simple linear regression. So that will be a continuous predictor. Okay? And later, when we get to the multiple linear regression, we're going to also introduce this two other predictors. One is rural, that's binary, whether the CU is in binary or in urban, whether the CU is in urban or rural area. And the other one is race, which is a categorical, unordered categorical variable. So those will be typical, I would say, types of predictors, like say continuous, binary, or unordered categorical. And so we're going to focus on the log income for now, just to cover the simple linear regression. And later we're going to look at, well, if you have other types of predictors, what you're going to do when you're doing your regression. Okay? All right, so that's the setup. And